transportation seminar. Before I introduce this honored speaker today, I'd like to talk about some logistics. And first of all, thank all of you for attending this seminar. And it is sponsored by our student ITE chapter and also the UTCs. We will have a presentation session, and we will also have questions and answers during the presentation. I would appreciate you could mute yourself, but when you start to ask questions, you can either use chat box or unmute yourself and talk to us directly. And please know that this session is recorded. So today we are very honored to have very well-known, renowned scholar, Dr. Larry Had from University of Arizona. I believe you all have seen his bio and intro from the flyer we sent to you, and I don't have to repeat him, but I just want to share with you about a couple of my feelings about this respectful scholar. I actually knew him a while ago, many years ago, and that time I was just like from a graduate student to a junior faculty, and the first thing I felt like he was a very approachable person. You know, if you read his bio, you know, he took positions up to all the way to the provost level, and you would think that you know, a person at that level is you know, really high up there. But he's very approachable, very supportive, and he stopped at my conference posters and talked to me, and I feel like very nice to be around of him. And another thing I want to emphasize is he is one unique scholar that has, you know, really transferred the research and knowledge into practice widely and made a great impact. If you see from his virtual background, that's actual streetcar, you know, one of his great pieces of work, and he's deployed that system that he developed, specifically MMITSS, across many places and made a huge impact. Everybody knows his work. So with this, I would just like to give the floor to Dr. Had, and thank you so much.
Xiaoping, thank you for the kind introduction. And I remember well that conference at Michigan where you had your paper about trajectories. And I've been a big believer in trajectories for traffic signal control. So I'm really a fan of your work. And so thank you. It's been fun to watch you develop. So today I'm going to talk about what's called the multimodal intelligent traffic signal system. And it really, this is it's a pool fund project. So these are my credits to the team. This has been funded since 2012 by the Connected Vehicle Pool Fund. And if you're not familiar with the pool fund, but FHWA and several departments of transportation put their money together. It's a partnership with the University of California, Berkeley PATH team, with Kunzu is my partner there. It's been great working on this, and I've had many graduate students and undergraduates involved in the project. But what the Connected Vehicle Pool Fund asked was they wanted to use connected vehicle technology to create a new generation of traffic control or traffic management system that really could provide priority for emergency vehicles, transit vehicles, and trucks, could do intelligent signal control, and then they asked for some pedestrian assistance to be integrated into it. So we started back in 2012, we did a ConOps and requirements, and then we did a demonstration in phase 2 that started in 2015. If I was going to have any gripe with pool fund, it would be that they have these large gaps between work years. So you get a bunch of students funded and then you wait a year or two and then you fund them again. It's a little challenging at times, but we built the prototype system and we deployed it and we tested it. We did tons of demonstrations and taught people about connected vehicle technology. And then what they asked us to do, which is really unusual for an academic project, is they said, well, it's really nice, but it's hardware dependent and we want you to be deployable. So can you turn it into something that's more deployable? And so we've had to go back and redo all the source code and documentation and things. And we're in the middle of a 90-day field test. With COVID going on, field testing is really hard. So some of the basic ideas goes like this. If you have a traffic system, typically if you're going to manage it, you break it into control sections, right? And maybe in this section of the network, you have a bunch of warehouses and manufacturing facilities, and the vehicles that are going to be traveling through there may be a high percentage of freight vehicles. So you might want to set up a hierarchy for control. Of course, rail crossings are first and then emergency vehicles, but maybe we want to give priority to freight platoons and then freight vehicles. And then maybe we want the signals to be coordinated, and then transit, and then passenger vehicles and pedestrians. And so that might be what the operating agency feels is their level of priority for different kinds of vehicles. Here's another section over here where maybe this is where there's a lot of transit and pedestrian, and we would want to give priority to transit vehicles, and then maybe strings of vehicles and pedestrians and passenger vehicles. And however they want to set this up, that should be there for them to decide. And in a connected vehicle world now, we would have lots of data to help us set that kind of a hierarchy up. The other thing that's really great in a connected vehicle world is that we can measure, or Wade Bin at Berkeley called it observing performance by mode, by movement, by section. And so we can get all the traditional measurements, but I want to introduce this idea of smoothness of traffic flow to you later today. So something that we call soft. So just a few characteristics. I think it's a little bit more of the history, but we use all the connected vehicle messages that are defined in the J2735 standard, basic safety message map, signal request, signal status message, and SPAT. ISIG really is what we think of ISIG as adaptive control, and it's a outgrowth from some work in the 90s on RT tracks that Federal Highway did. And then if you're familiar with roads, that P2 Merchandani led the effort on, and one algorithm in roads was called the COP algorithm, Surjit Sen and I wrote, and then OPAC with Nate Gardner. And so the ideas around that component are really motivated by them, and Yiheng Fong, a student, he modified it to do some things with the lemma zone. And then the priority work really started back with a project called NCHRP 366, which Tom Urbanick, Darcy Bullock, and I and Doug Getman worked on, and that became the NTCIP 1211 standard, okay? And really, it sets up the framework. And then I've had several students, including Ching and Mehdi, and now Debashish working on this priority-based control. And then the Sarah Kosarabi was a student who did the PED-SIG, and she works at CAPSH now, and they've taken it and made it into a product that's out there. So just to sort of frame this up, when a priority eligible vehicle, whether it's emergency vehicle, freight, transit, coordinator, and I'll talk about that in a minute, a platoon of vehicles or string or another intersection, gets in the range of the RSU or wants to communicate with the RSU, there's this map. And so vehicles receive the map, and the vehicles will compute their position on the map and use that to estimate their estimated time of arrival or their desired service time. Okay, now if you're shaping the trajectories like you guys do in your research, that time may be the departure time in your algorithm, right? Then the vehicle sends something called the signal request message to the roadside. The infrastructure responds back with something called the signal status message, which really is an acknowledgement of the SRM. If you send me a desired time of service, I'll send it back to you from the infrastructure to make sure that we're in agreement. Right, then when the vehicle passes through the intersection, it can send a cancel, and then the infrastructure can go back to other priorities. And this is really the use case for priority-based control. Who can ask for priority? Well, all these different kinds of vehicles, and coordination could ask for priority, and I'll explain that in a minute. And then these platoons and strings, which we're working on now, how to get this done. And then queues and other intersections. We did for Utah DOT, who's a big user of MMITSS, we did a peer-to-peer capability for them to kind of give more headway into getting the priority requests in the system. So this is the architecture for deployment. And this is really kind of funny because I drew this diagram in 2011, I think, and we haven't really changed it. You start down here with vehicles, and we have two kinds of vehicles, equipped vehicles and unequipped vehicles. And an equipped vehicle has an onboard unit that can talk to a roadside unit. right? And that roadside unit communicates with something we call the MMITSS roadside processor. And this is think of this as an edge processor. And actually we're working with Intel. They're building something called a smart RSU that is an edge processor along with a radio unit. And then that's what communicates with the traffic signal controller. And the same way with the non-motorized travelers, they might have some type of nomadic device like a smartphone, right, that could connect into the system through the cellular network or Wi-Fi or somehow. Maybe someday with 5G, we'll have a more direct link there. And then that closes the loop over there. And then, of course, there's security that you have to take care of up at the top. And so I'm happy that this diagram has survived over the time. Our MMITSS architecture, this is our software architecture. I like to talk about this before I talk about the algorithms, because then you'll kind of see where things fit in. And so we have a MMITSS roadside processor, that's that edge processor, and then we have a server that's available, and then every vehicle has a vehicle processor. And because in the phase 3 they want us to be agnostic to the brand of the RSUs and the OBUs, we used a standard interface that Federal Highway defined, this RSU 4.1. Oh, I didn't mean to do that. Interface to be able to talk to them. And then we have a little display. I'll show you that in a second. So let me talk about the roadside processor. So the roadside unit is really just a radio to us. There's no processor in this unit, right? And so we have this message transceiver that encodes and decodes messages. And we do this in this component because as the standard evolves and changes, we just have to update this component. And then these messages inside the box, I've lost my mouse, but the priority request server receives signal request messages and turns back signal status messages, but they're not formatted as messages. They're just JSON strings that we pass around between the components. The priority request server is responsible for taking the requests from all the different kinds of vehicles and managing them and setting up that hierarchy. And then really what I'm going to talk a lot about in a few minutes is this priority request solver, which solves an optimal scheduling problem to be able to accommodate the priority requests. And those requests could come from coordination. The two components in the middle, the ISIG, the traffic control and trajectory aware, are dashed lines because in the phase 3 effort, we haven't put a lot of effort into redoing all that code because in our field deployment, we just don't have the market penetration that's really required to accommodate doing some intelligent control or adaptive control with the small amount of data that we have available. We have 15 vehicles, and that's not enough in a network. Then we have something called the map spat broadcaster, which takes spat data out of the signal controller and merges it with the map and sends it out over the air. And then all the components are able to talk to the traffic control interface, which is the business logic of talking to the traffic controller and works through NTCIP or SNMP, if you're familiar with how NTCIP works. We run everything as, yeah, go ahead.
Did you show the demonstration or something? I'm not sure if others saw, and I saw a blank screen just now. Whether others have seen.
Yeah. No, you know what? Something the Teams window popped up and showed me everyone's face, so I didn't show a demo or anything. Is that what you saw? Is it back to you seeing my screen?
I think somebody else shared something, so you might have to reshare your screen.
Okay, so now how am I going to do this? I'm going to stop sharing. Okay, stop sharing. Okay, and now I'm going to share my desktop.
Okay, all right, sorry about it.
No, that's good. Thanks for letting me know. It's going to be much more meaningful.
We can see your presentation slide. Mm-hmm.
Okay, so this is the MMITSS roadside processor, which is an edge processing device. These are the different software components: the message transceiver, the priority request server, the coordination request generator, the solver, which is really a solver in a true math programming sense, which solves an optimal scheduling problem. Traffic control interface, which knows the rules of talking to the signal controller, and then we use SNMP and TCIP objects to talk to the controller. Everything is run in a Docker container. Okay, so this really helps us out when we're doing simulation, because we can just run a bunch of Docker instances using Docker Compose and have all the different intersections running when we're doing simulation. And all the configuration data, right now it's in 3 files. We always are trying to get everything into one master config file. We have a web interface for managing the system, and then we have a way of exporting the data. And we export data in real time, we collect it locally, we push it to a server, and then we push it up to the cloud where it's available to use. And then on the vehicle side, it's exactly the same message transceiver, because we want to get rid of all those nasty rules of encoding and decoding messages, right? And then we pass the same kind of JSON objects off to something called the priority request generator. And the priority request generator is this part that's keeping track of the vehicle position and taking the position and seeing if there's an active map. And if there is a map and you're on the map, then it generates the request for priority. All right, so it's the vehicle side logic. And if it's an emergency vehicle, we have to have an interface to the lights and sirens. So we have a lights and siren manager. And then because we don't have real-time offloading of the data, we just do compression of the data that's there, and then we offload it at different times with a laptop. We have this display that we've created that's really just intended to help us when we're out in the field testing. So it shows you in the upper left-hand corner the stat data with the minimum and the maximum phase times and what the display is, which depends on what lane of the map that you're in. Shows you what the signals are doing, what phases are green, yellow, and red, and whether there's pedestrian service going. For the host vehicle, we have what kind of vehicle are you, what's your temporary ID, your speed, and information like that. There's a couple of indicators at the top. So when you're on a map, at the bottom, you'll see we have a list of 5 maps that are available. And when we receive a map message, we retain that for up to 5 minutes, 300 seconds. And then we delete them to keep the cache of maps cleared. But when we have a map and we're on the map, we show it as being on the map. And then when we send a request, our request will be active. Then the active request table, the signal status message comes back out with all of the requests from all of the vehicles. And so there's an EV vehicle that's requesting, and a transit vehicle and a truck vehicle. And so whether they're rejected or granted, how many messages have been received, what lane of the map they're on, what their arrival time is. And then if there's other vehicles in the area, we call them remote vehicles, we get their basic safety messages. And so this has been a really great tool when we're doing demos or we're out in the street testing, so we can make sure that everything is on the vehicle side, looks good. If you're interested, you can just Google MMITSS and GitHub, and you'll find all the source code. We try to keep it up to date. We have a new release every so often. We're about to have one next week, has some new features in it. There's some common components. There's a map engine and a message library that Kunzu at Berkeley developed that are really, really useful components if you're dealing. So you don't have to deal with the map message itself. You can just call the functions in the library. And so this was a great contribution from Kun. And then if you want to run things and you don't want to be the software engineer that builds it, you can just download the different Docker containers. And so there's x86 base for doing simulation. There's one here that says updated 5 years ago. That's the phase 2 version of MMITSS. Then there's the ARM base, and we use ARM base for both the vehicle and the roadside unit processors. And so you can download these. Okay, so that's too long about the system itself. Now I want to talk about sort of the basic principles behind priority-based traffic control. And so I suspect this group knows a lot about traffic control, but this is a diagram that I use to describe some of the terminology. And so this is an intersection. This is in Noblesville, Indiana. This is from a project Darcy and I worked on. But down here in the corner is the dual ring 8-phase traffic signal controller, which is the standard in North America and used in many parts of the world. Other types of controllers have other kinds of logic to them. So we really focused on this because this is the most common one in North America. So when phases 1 and 5 and each of the rings are timing, then that's when we might have, say, these left turn movements. One of the left turns might gap out because there's no more cars over the detectors. So phase 5 gaps out, we move on to phase 6, and we can have phase 1 and phase 6. And then after a while, maybe phase 1 reaches its max time and we get to phase 2 and phase 6. And then a little while later, they're done serving for whatever reason, gapping out or maxing out or for other strategic reasons. They jump what's called a barrier. That black line in there is called a barrier. So we jump the barrier and we do the same sort of logic on the side street. Now 3 and 7 are the left turn phases. And then we go to 4 and 7 and maybe 4 and 8. And then the whole thing goes back around and starts over again. And so look, there's lots of kinds of ring barrier controllers. Our company had one that was 20 rings, 40 phases, and 26 barriers. 26 is a magic number because we represented them by letters, A through Z, and so that's why we were limited. But what I did was back in, when I left industry and came back to academia, is I was really worried that we had this software, but we didn't have an underlying model. So a model of this dual ring controller is this precedence diagram, and this shows 2 cycles of what I just showed you, but it represents it in a more of a mathematical way where we could then bring it into an optimization problem. And so it's the same thing. Phase 1 has to time before phase 2 because we can only have one phase active in a ring at a time. Phase 5 and phase 6, and then when we go to cross the barrier, we're going to get to 3 and 7 and 4 and 8, and we repeat this over and over again. This sequence repeat. So now I have this graph structure, a precedence graph, that we can do different kinds of controllers with precedence graph, but we're just doing this dual ring 8 phase for now. Every phase in the precedence graph also has its own precedence graph of these sort of intervals that are there. Like you have to have a minimum time. Minimum is a safety parameter in a traffic controller. And then you have an extension period where if there's detectors, you may extend out for some amount of time for every detection event. You could have a signal control prioritization in the NTCA P1211. We have an interval you can extend there. If the pedestrian is serving, then you get the walk and the flashing don't walk, and then a don't walk interval. And those, the walk and flashing don't walk have to time before you can terminate the phase. And then some controllers have a minimum, an alternative minimum green time. And so these really constrain what we can do to the phases in terms of stretching and compressing them. So you take all these structural parameters, whether phases are in use or if they're recalled or omitted or whatever, you take the data that goes with the phases, the timing values that are in the database, you take the real-time data that goes with it, and then we can form this precedence model. And that's what we're trying to do. I want to represent things we call priority requests that come from all these different kinds of uses and vehicles. But in this precedence graph, I show a request that says, I want to serve phase 8 at time 38. So if you think of now as time 0, 38 seconds from now, I have, say, a transit vehicle that wants to go through the intersection, and it's going to go through on phase 8. Well, phase 8 is here, or it could be in the next cycle down there, right? And so I want to make some decisions about getting to phase 8. So there's delay before it could be served there, or there's this amount of delay. And so clearly, the obvious thing is I want to get phase 8 green as soon as possible. So if I could compress this down a little bit, get there, I would reduce the delay for that request. But I can have all kinds of requests, and we've done this. We've had requests for every phase occurring randomly throughout from all different kinds of vehicles. The problem is that this is a math programming problem. It's a mixed integer linear program, and it takes time to solve. And so we can't really accommodate an infinite number of requests because every request adds to the problem. This is the model formulation. I'll go through this a little bit, but we minimize what we call the multi-modal delay, and that's the delay from transit, trucks, and emergency vehicles. We have coordination delay, which is another consideration. If we want the signals to be coordinated, we treat that as a form of priority. And then we've added this other term on the end called actuation flexibility. And this goes to wanting to have flexibility in the signal timing to allow phases to gap out or allow phases to do their natural behavior with the vehicles that are locally present. And I'll show you how that's in there. And notice it's a minus sign and a minimization problem. So we want to make that as big as possible. We want as much actuation flexibility as we can when we're dealing with all of these delays. And so then this is subject to the precedence model, the phase constraints from that I showed earlier, and then something I call phase service selection constraints. So the precedence constraints are easy. These are nice, simple linear equations. Anybody could write these. This is a no-brainer. Just represents the precedence graph. The phase duration constraints, while it may look fancy in this diagram, really just takes into account all the different parameters, the flags, and whether there's real-time calls to get a minimum and a maximum green time, right? So there's some logic that are these functions that take these indicator variables, if you will, and develops a minimum and maximum green time. And that's really all that this logic does. And then the phase service selection constraint. So if you remember that picture where I had phase 8 and I either had to serve it in the next cycle or the one following it, you could think of these black lines here in the precedence ones. I've only picked out the phases that I want. And then I can either be, the request can either be before the service interval or during the service interval, right? And so this is a 3-cycle model. And this assigns, this is an assignment, so it's a binary variable assigning it to one of these intervals, and we're going to try to assign it to the different intervals in a way so that we can minimize that delay. And so that idea can be written as a set of constraints using the big M method, and it just takes a little bit of time to figure out how these represent that, and they can be simplified and reduce the number of variables, but this is the most descriptive way we've got of showing it. Okay, and so then we got the delay, right? And so don't freak out and go, oh no, it's nonlinear, but this is just a representation. But we have the delay of all the priority requests between the time when the request is the estimated arrival time and when the phase starts serving of where we can have those requests, right? And then we've rewritten this so it's a linear problem by moving this into the constraints and using dummy variable type logic. That everybody that does math programming knows how to do that. Ching came up with a nice way of representing these diagrams. Across the bottom is time, and up the left side is each of these intervals represents phase 1, phase 2, phase 3, phase 4, phase 1, phase 2, phase 3, phase 4. And on the other side, it's phase 5, 6, 7, 8, 5, 6, 7, 8. And so if we think of this orange line being the amount of time that phase 1 times, well, its minimum time is here. Here's a request for phase 2, and we give the request some duration now for uncertainty. And so there would be a little bit of delay before phase 2 started to serve that. Phase 2 times, phase 6 times, then phase 3 and 7 time. There's a request here for phase 7, so we hold on to that phase for a while. And so this is a nice way of visualizing the solution to the problem. I learned a long time ago, when I go and try to put this stuff in the street, if I don't develop some tools for communicating with the traffic engineers and the technicians, they just look at the equations and say, I have no idea what you're talking about. And if I don't have an idea what you're talking about, you can't do it in my street. This is a kind of an interesting graph that Mehdi drew, and this has to do with what we call left critical points and right critical points. If we want to get where we can serve this priority request with no delay, what is the area, the flexibility, if you will, that we can have before we get to serving that? So this says that phase 1 can time any time between this left critical point and the right critical point. Phase 2, depending on when phase 1 ends, would be between its start time and this right critical point, and so on. And so in that optimization problem, the volume of this area is actually what is in that term, and we want to make that as big as possible, because then we can actuate or use the COP algorithm or whatever to accommodate the vehicles that are arriving that are not priority eligible vehicles. And so once we solve that problem and we get a solution, we need to be able to understand the schedule. And it turns out it's a little bit complex, but here's we'll translate this into how we talk to the traffic signal controller. So we can call phases. And so on this graph, this time phase diagram, you can see these little C's, and those are the call events. And then when we get to the right critical point, we have to force the phase off so that we can move on. So you'll see there's some FOs in here. They're not super clear in this diagram, but that's where we actually have to force the phases off. We could hold a phase, like we might hold this phase green that would go longer than the time. We actually hold it to the left critical point, okay? We have to hold it, and then we have to clear that hold. And if we wanted to skip a phase, we could omit the phase. And so these are the NTCIP commands that we use when we're talking to the signal controller, and that maps on to the solution that we get and tells us what do we want to do. if we want a phase to be able to gap out, we just don't hold it and we don't force it off. We let the natural phase behavior take care of that. So go back to the model, and now you've seen the multimodal delay, and you've seen the actuation flexibility, and I hope you have some appreciation. I know that I'm going fast, but I want to leave time for questions, some appreciation for the way the constraints work in the problem, and we're there. And so what I want you to think about now is think about these as being these weights, these parameters in the objective function as being sliders. And so these are the controls that we give to the traffic engineer to set up their policy. So in this example, I've got coordination have a very low weight. The beta here has a very low weight. The actuation flexibility, I still want quite a bit of actuation flexibility, so we put it around 1. And we're really interested in multimodal delay, and emergency vehicles by far get the most. Matter of fact, we override the other vehicles, but in this example, freight is more important than public transport. This is actually a slide for a talk I'm giving it next week in Australia. So we call it public transport. But this idea then gives the traffic engineer a way of controlling this. And so Mehdi Zemanapour did a very nice example that illustrates the ability to shape, if you will, the performance surface of this system. So in this example, we're going to run this simulation many, many times, but transit go back and forth east to west and trucks go north and south. And so in this particular example, there's 2 transit vehicles and a truck. This is our active request table. This shows the estimated time of arrival as a range and what phase they're requesting. Okay, and so we ran this simulation with lots of different weights, and in this we're only looking at transit and truck. Okay, because if we have an emergency vehicle, we don't consider the transit and truck, except we do dilemma zone protection for trucks. But we varied the weight. So transit was 1, truck was 0. On the other end, transit was 0, truck was 1. And we used a bunch of different combinations in here. And then each one of these points represents a 30-minute warm-up and a 1-hour simulation and 10 replications of the simulation model of that intersection that I showed you before. And this is, you know, a contrived example that will allow us to show that by changing the weights, we're able to minimize the transit delay, but then as the transit weight tends back towards 0, okay, or relatively towards 0, its delay goes up. And here's the freight weight going the other direction as freight becomes more important. So we really can show that. This green line represents a delay to the other vehicles, and the red and the green line show what happens if we didn't have any priority at all across the weight. So we're doing a lot more with this sort of multi-criterion decision making and looking at the Pareto frontier and things right now. Debashish Das is doing that, but we're able to demonstrate that the weights can be a powerful way of shaping the priority. Take a breath. So let me talk about coordination. I really think coordination is a form of priority. If you go to the way traffic controllers have been built over the last 50 or 60 years, they have their coordinator. When you do preemption, you throw coordination out the window. You do whatever you want to do for preemption, and then you come back and you seek your transition back into coordination. But what if we just thought of coordination as a form of priority, where the goal is to get the phase green when a group of vehicles is going to progress along the coordinated route, because that's what we really want to do. We want this progression along a coordinated route. That's why we use coordination. But priority's goal is to get the phase green when a priority eligible vehicle wants to progress along its route. And so few change of words and they're the same thing. So what we can do is, and I'm going to use this example, this is Speedway near the University of Arizona. We developed a coordination plan with an offset of 0, 28, 48, and 68 for vehicles to progress down Speedway. We will look at each intersection, and what we do is we schedule for 2 cycles the coordination event. So this is phase 2 to be coordinated with 0 offset, right? And then 110 seconds later, 105 seconds later, you'll see those requests again, and then you see the lines that kind of indicate the region where the left critical points and right critical points where we want to serve the priority requests. And so this is for the first intersection, this is for the second intersection. These vertical lines throw people off, but we don't have a phase 3 and a phase 7 at that intersection. So it just skips that phase and moves on to the next ones. And it shows that we're going to be in coordination, and we've got a little flexibility that's there. Here's the 3rd intersection, and here's the 4th intersection that's there at Park. Here's a time space diagram of the solution to each of the problems at each of the intersections. Shows the direction of travel from the bottom to the top. We get a nice green band through there. Looks pretty good. We wanted to compare it to traditional coordination to what we're doing. So again, we ran the simulation, I think that 10 times is what he ran it for an hour. And we collected the travel time on the different movements at the intersections. And we compared them between the two, and we represent it here on a radar diagram. So Campbell northbound through movement, northbound right turn, northbound left turn, and we wanted to see what the difference was. And so here's the eastbound left turn, the eastbound through, the eastbound right turn, and the southbound, and then the westbound. And so they at least have the same general shape. This is the next intersection, and they don't like westbound left turn there at that intersection. So again, I think we were able to capture the same sort of traffic behavior, the same at Mountain and Speedway and the same at Park. And it's not identical, but my claim would be that our simulation testing reflected that it really is essentially the same. We need to show something with priority and coordination. I'll show you that in a second. Where we've talked to the people at camp that are doing TOSCO about adapting the signals with these platoon information going through there. And then UDOT has asked us to do some adaptive coordination based on the flow of vehicles in the corridor. Like if you get an early green and you release the platoon, then you should schedule the downstream intersection to be a little bit earlier. That's there. So this is just a simple example. I'm going to stick this yellow truck on there. So it was going to arrive right after the coordination event. At the first intersection, at the second intersection, it was going to arrive a little bit early, but we're still able to accommodate serving both the truck and the coordination point. Here's the third intersection, and again, it's a little bit earlier than coordination because of the way the truck travels. But again, we're still able to accommodate all of the requests. And then this is the fourth intersection, and actually at this intersection, we delayed the truck a little bit, but the coordination was able to be accommodated. Of course, this would change if we changed the weight for truck over coordination. I don't remember exactly in this experiment what Devashish used. That's there. So again, I think we've shown that they're kind of equivalent. We're in the process right now of running this in the field. We haven't been to the field test in quite a while because of COVID, but we will be out there on Monday next week. And so we'll be running a bunch of vehicles. And so I'll have some data from that. Real quick, I just want to talk about assessing performance. You guys know all about trajectories. And so having trajectories means you can compute all these measures. I like Weiben's way of saying is that we observe them. We don't have to estimate them. Okay. And then I want to talk about this measure of softness. When you're moving trucks, especially, and other vehicles, but if you're moving trucks, you really do care that they don't accelerate and deaccelerate. So here's 4 different speed profiles of the vehicles. The first one looks like the vehicle goes along at about 15 meters per second, pretty good speed. The second one over here, a lot of stop and go behavior. Here's a third one where there's a little slow down and speed up, but looks pretty good. And then this one has a little more variability to it. And so we looked at these and we computed the sum of squared errors from constant speed, and we're trying to think of what's a good measure. And this is where we came up with this idea of this measure we call soft. And I'm going to skip this slide and I'm just going to go to this slide. This shows two trajectories. So think of these as sample points of trajectories over time. This is a very smooth looking trajectory compared to this one, which is a lot of stop and go. And then, so if I look at this from a signals point of view, I just look in the frequency domain, take the Fourier transform, and I know that a constant signal would have all its power centered right around 0 frequency. Where if there's a lot of harmonics in the signal or a lot of other variability, I expect to see more power distributed at higher frequencies. And so that's what we've done, is we've really just taken the ratio, 1 minus the ratio of whatever the power distribution is to the power around 0. And so that's this ratio here of the square root of the squared powers that's there, multiply it by 100, and we got a measure of softness. So these are the speed profiles from lots of simulation runs and the free operation, coordination, and just resting in green. We expect resting in green to be pretty good, but traffic dynamics cause some speed variability that's out there. Coordination, if they were progressing through. So clearly a lot of vehicles stop at these first two, but more get through here than they did when they were free. So they arrive at the first signal and then they get into the coordinated flow. Here's what their trajectories look like and their value of soft. So these are a bunch of trajectories. And then this is the soft value for each one of these trajectories that's there. The same thing here when it's in coordination. So you can see the pattern in the soft that's there. And here's if the trajectories are all mostly just flowing straight through. And so we compute the soft measure. This is 73, 89, and 99. And I believe we have a measure, we can measure sort of the smoothness of flow. So one question we ask is, what happens if we sprinkle trucks in the flow instead of just regular cars? And so the red dots in here, the red dots in here represent when we had 0% trucks, 20%, 40%, and 60%. And truck dynamics are really quite different than vehicle dynamics, right? And so we go from 88 to 83 to 81 to 76. And so clearly we're getting less smooth flow, more trucks that we have. And so this is important. And then here's testing for significance of does the percentage of trucks actually impact the soft factor when we're analyzing smooth flow. So the reason we're interested in this is we have this project. There's 19 traffic signals along this corridor in Maricopa County. And there's two giant Amazon facilities in Phoenix. One is at 75th and Roosevelt, and the other's down here on the other end of this corridor. And they actually operate a fleet of 40 trucks that go back and forth all day long between these two Amazon facilities, balancing inventory to help make sure that they have what they need to get things out. These are, a couple million square feet facilities that are there. And so the goal of the project is to use MMITSS and use the priority for the truck vehicles to improve the flow through the corridor. So this corridor got really torn up. Every time a truck stops, it tears up the pavement. Every time it accelerates, it tears up the environment. And so we improved the smoothness. You can see the smooth values. I don't have a summary of the numbers, but we look at the truck speed and we look at the delay of the truck and the stops, these classic measures through there, and MMITSS makes a tremendous difference on the flow of the trucks going through the corridor. So we reduced the stops by about 20%, and which is really a good outcome. We only ran MMITSS on 8 of the 19 signals that's there. So as Xiaoping said, MMITSS has kind of grown up. It's got to get out of academia at some point. I'm actually tired of doing projects in different places. I'm ready for some consultants to own it or something. And I'm not interested in starting a company. I did that once, and that's hard work. But we have 5 projects in Maricopa County. We have the Smart Drive testbed, which I'll talk about in a second. We have the Loop 101 mobility, that's an ATC MTD project in Scottsdale, where we're doing some transit priority. We have the freight corridor I talked about. We have 2 transit projects, one in Tempe near ASU and one in Mesa. The PATH team has their version of MMITSS that they operate on Camino Real, Kuhn and his team. We have 3 traffic signals in Portland, on a streetcar route in Portland. UDOT has 137 intersections running a version of MMITSS that they created called MMITSS Utah. We're doing a demo project in Madison with 16 intersections. And then in VIA, they used MMITSS in the early CV pilot, but they actually have come back and we're going to do some congestion mitigation by using MMITSS in an area where they're dumping some vehicles off. And so I put the software architecture on here and a picture of our web interface on here. I think MMITSS is now to the point where people can take it. It's open source and they can take it and do things. This test bed that we have in Anthem, Arizona has been really important to us. It's 11 signalized intersections where we run MMITSS 24/7. We're in control of the signals. Not a lot of places in the country, not a lot of agencies that would probably let some academic control their traffic signals, so we're lucky to have this. What I love about this place is it's a developed community, and there's 25,000 residents and 10,000 vehicles that are registered there, and they have to go through our traffic signals to get in and out. There's essentially a wall around this community. And if I could get, I always say this, if I could get 2,000 or 3,000 of those vehicles equipped, then we would have 20 to 30% market penetration, and we could learn some really important lessons about that. And we've done demos for lots of different people. We have great partnerships out there. With that, I did that really fast, but how about questions? Anybody?
Thank you. Very nice presentation. Learn a lot. Any questions from the audience? Please unmute yourself and speak out or leave the messages in the chat box.
Maybe I'll go like this.
Hi, Dr. Head. I'm Saeed, a PhD student from USF. Thank you for the great presentation. I have just one or maybe two questions. So my first question is, you present some results, some improvement in travel delay when using this MMITSS strategy. So I was wondering, so when you're you had a slide like showing the results of working on that Amazon project, right? So I was wondering, when you're comparing to the delay, you're comparing it with which scenario, the existing scenario or the optimized fixed time without addressing priority?
So the current scenario, the way that they operate the traffic signals today.
Right. So my question is, maybe is it possible that so since addressing some of the priorities would give some weight to some of the vehicles, and there are more vehicles that do not get benefit from this priority that is requested by other trucks, right? Because they might have an extra delay since we are switching the signal for those priority vehicles. So I was wondering, is it possible to compare the result with a case without using priority, but sort of trying to optimize the coordination between signals? So when you compare your result, you compare it with the case that all the signals are in the current situation, but you just added the priority, right?
Yeah. So Maricopa County DOT operates those traffic signals, and they have a very good traffic engineer who works very hard to make sure that the coordination plan that she develops and deploys out there operates efficiently, right? And so they're always out there driving the corridor and doing things and monitoring it in their traffic system and such. And so I feel the way that they currently operate it is pretty good. Maybe we could optimize it and do a little bit better. When we apply priority for the freight vehicles and we reduce their stops and delays, there's vehicles that are not priority vehicles along the corridor that are going to get benefit also because they're traveling along the corridor, and there's those that are going to be impacted negatively by it. And I would expect that would be a negative impact, and it would be measurable. Anytime you shift the priority from one mode to another, or from treating everybody the same to emphasizing priority for one mode, you have to have a negative impact on somebody. Now, I'm sure you read the literature and people are like, we were able to get priority and have no impact. Well, I don't actually believe them. They just did a bad job of the original traffic signal system. So. Right.
Thank you. Yeah, that's great. And just for clarification, so the delay the reason I'm asking is because my research is similar, so I'm curious.
Okay.
The delay that you present is the delay of the truck vehicles or the delay of the whole traffic?
Just the truck vehicles.
I see.
Right. So yeah, your question is right. I should be showing you the impact on the other vehicles, what the delay is.
Yeah, I was wondering, while this is beneficial for those trucks, it might not be fair for the whole traffic, and it might be hard to, apply them.
So the question of fairness is an interesting one, because we're not necessarily trying to be fair. We're trying to operate the corridor for its particular purpose in the best way possible. And so the agency decides, well, because we're moving all this freight and we want to prolong the life of our pavement, the right thing to do is try to reduce the number of stops and such of the trucks, right? So fair might mean we make that decision and we delay the other vehicles. That's where this sort of policy-based hierarchy comes in.
Thank you so much. Thanks for the great presentation.
Yeah, thanks.
Thank you. Other questions?
Hi. I just want to follow up what Saeed mentioned and your answers, because I think the objective function is delay, but if we transfer everything to including like environmental impact, including health or whatever, when we can transfer that, then maybe the whole thing actually have been improved, not only just for the truck, but for other things as well. So from that point of view, I think the fairness and equity is actually there. This is just comment.
No, I think it's a very fair comment. If we could capture all of those different effects in the objective function and still solve the problem in real time, remember we actually implement this on hardware in the field, that becomes a constraint. So you know what, I know that there's some really smart people out there that are doing deep learning and other kinds of things that are gonna figure this out, and they're gonna do better, and I'm all for it. You know.
Yeah, but it's very impressive, as you mentioned. This is like the academic controlled the traffic signals, and that is very impressive.
Yeah, I've been very fortunate that they let me control the signals up there. I've also been talked to by the sheriff's department. We froze a signal in red one day, and the citizens called the sheriff, and they came to visit me. They were good natured. They just said, "Put your hands behind your back," right? And then we explained what we were doing, and you know, we've learned a lot of lessons. The test bed is about 2.5 hours from the University of Arizona. It's north of Phoenix, and we're in Tucson. And so early on, my graduate students learned that if we go up there to test something and we find a problem 30 minutes into the testing, that's a long drive to find a problem. So we do a lot of simulation testing. We do a lot of testing here on the street in Tucson, where we're not actually controlling the signal, but we set up an RSU and a signal controller in a cabinet that we have, and we drive. And so, yeah, my students have a lot more real world experience than some PhD students. So
that's great. That's great. Yeah, actually, we worked with the Traffic Management Center of the City of Tampa, and we actually have a small lab. I think Dr. Lee was involved. Dr. Lin from Carter is involved. So that could be also a good, you know, test bed for whatever Dr. Lin's and Dr. Lee's groups are doing. Yeah.
Yeah. You know, one of the things that I kind of hope, why I talk about our software architecture, is that maybe somebody will use our framework and gut some of our components. We rewrote a lot of the stuff in Python. So it's pretty easy to just take our template and gut it and put in whatever algorithms and things you want. But some of the, you know, like talking to the signal controller, why should people have to reinvent that? That should be available to be used. So
yeah, that's great technology transfer that benefits so many different cities and agencies. Yeah, great.
Yeah, so my tech transfer people think I should start a company and license it, all this, and I just want to give it away, right? I mean, look, there's not that much money in this industry to be worth this. It's not Microsoft. So somebody has their hand up.
Let's see. Go ahead, shall we, Tom?
Yeah. Hi, Dr. Hyde. And
how are you?
Yeah, good. And so it's very impressive presentation. And I just have a question about the V2X communication part. I think most of your application is rely on the stable V2X communication. So have you considered the communication range, communication delays, these kind of factors in your field experiment?
Yeah, so I could show you some data, but our range, each RSU has somewhere between 800 meters and 1 kilometer or more of range. So it covers the network very well. The reason that the range is important is because the greater range you have, the more future look ahead you have to be able to optimize. The other thing that goes along with that is the map message has to extend out as far as possible. Because if you don't send a signal request till you're on the map, you have to make sure you build the map to go far enough out. And then the latency, to be perfectly honest with you, for our application, since this is not safety-based, latency is not that important. If it happens within a second, I'm pretty satisfied. And we're using DSRC, and the latency's, you know, on the order of 7 milliseconds or something. I'm not worried about it.
Yes, since based on my experience, as the distance, I mean, between the OBU and ISU become longer, the delay, I mean, can significantly increase. So I don't know this kind of factor whether will impact your final results about the performance of your algorithm.
That's a good question. I have not noticed any significant delays at the you know, sort of the range, the edge of the range, the edge of the map. turns out to be the key point. So,
Okay, yeah. Okay, thank you.
I guess you can add more RSUs along the roadways to relay the information if.
Yeah, then the logic has to get a little more sophisticated because, you know, you're dealing with multiple radios and multiple things. And, but the basic model doesn't change. It's just that the handling of the messages and assignment to say, this is who you should be talking to and this is what you should be doing. So.
Mm-hmm. So yeah, just the one more question. So it's in your application, it's centralized control, right? You have one facility and control all the, I mean, behavior of the vehicle in the range.
Well, no, we have an edge processor at every intersection that does the processing for that intersection.
Okay.
So it's a really interesting question because for Madison, they don't necessarily have the same edge processor capability that we have. We run a board that Econolite produces called a CVCP board at each of the intersections. It fits in the controller modem slot. But Madison didn't have that. So we were looking at running everything as a server. And so we actually took the Docker images and ran them in Docker Compose, and we can run everything on the server and it really doesn't make a difference, except I'm worried about the network connections. So if there's network latency or drop of connections, we didn't necessarily engineer the communications of between the different software components to handle the loss of communication.
Okay, yeah, thank you.
Thanks. I see another question from the chat box. Does the algorithm serve the requests in a first to come, first to serve manner?
No, thank you. I love this question. No, we serve them all at the same time. Okay, so all of the requests, if we had 3 buses and 5 trucks, we'd serve 8 requests. If we have coordination requests, we serve coordination, buses, trucks. If EV comes, we override the other requests with the emergency vehicle, right? And so we cancel those requests and we only deal with emergency vehicles, but we can deal with 2, 3, 4 emergency vehicles at a time, which is different than your preemption in a signal controller today. It's first come, first serve.
Yeah, just to follow up on this, I think because it's a continuous process and vehicles continue to come, do you have like a rolling time mechanism, or how do you sort of like segregate the vehicles in groups so you can optimize them?
Yeah, so anytime we get a new request and we add it to the active request table, we resolve the problem. Okay. Anytime a request gets updated, because if a vehicle changes its speed and changes its estimated time of arrival, or if a vehicle cancels and we change it, we resolve the problem. If we have active requests and we haven't seen anything for 8 seconds, we resolve the problem.
I see. It's sort of like it's event triggered.
It's a rolling horizon event trigger. Yeah.
Okay. Any other questions? All right. So one last question. I think I like that your visual presentation, graphic presentations of the model, and it really sort of like made complex problems easy and intuitive, and I think so looks like the path. The idea is like you add some critical sort of like intersections and doing the optimizations on the paths in between to minimize the work, right? So it's like a hard constraint. Add some either time windows or time space. I would say time space critical points, right? So that is very. So do you just fix those points, or you these points also have windows you can move around?
Well, the critical points are the result of the optimization problem, and they're generally driven by constraints in the controller, like the walk and the don't walk time, or the minimum green time, or by the you have to leave now, or you're not going to get to serve that later priority request in time. So those are the 2 factors that really affect the left and right critical points.
Okay, so they're exogenous parameters or optimization variables?
Yeah, they're parameters that the optimization model is parameterized, and those parameters go in. The other thing we do is that we reread those parameters from the signal controller using NTCIP periodically, because if the traffic engineer went out and changed the minimum time from 7 to 15, which she did, we really need to know that, because we can't be trying to make decisions with the 7 when the real parameter is 15.
Okay. All right, great. So it looks like we're about the time, and again, I think this is a very nice presentation. It's really a masterpiece work that goes all the way from the depths of the math to the transfer of technology and impact to the society. I really enjoyed this presentation and learned a lot. I want to thank Dr. Head again for his great contribution, and thank all of you for your participation. And next week will be our spring break. And I think after spring break, we will have another presentation by Dr. Mike Cassidy. I think so you're welcome to dial in, and well, thank all of you. Hope you all have a great weekend.
Thank you for inviting me. It was great.